in the motor, I had a DC field that was created by these magnets. So real quick, north to south, which way does the North Pole, South Pole, which way is the field going? Well, all right, you guys are doing it for the wire, right? But if I have two magnets here, the field goes basically from the north to the south, right? What happened if I had the magnet by itself, the fields would go north and they would re-enter at the south, right? But when I put two of them together, there's a B field that basically, once they get close enough, there's a B field going from the north to the south. All right, so this would be our B field. All right, the current's going to go that direction out of this battery. So yeah, there's going to be a magnetic field going around it. What's going to happen to that wire if I set things up like that? What's going to happen to that wire? What will it do? Well, there'd be I got the battery here with a voltage across it. That's what's pushing the current through this thing. What would happen to the wire if I placed that wire in a magnetic field like that? It should move, right? And how do I figure out how much it moves? How do I figure out the force on that wire? That's why I wanted to do DC machines here in the middle, because they're really easy to understand. They'll help you understand the synchronous motor a little bit better. All right, so how do I figure out the force on a wire? You guys learned that in physics. If I put a wire inside of a magnetic field, there's a force on it. How do you figure that out? Force equals what?
E times what? Something with magnetic field, right?
Something with magnetic field? Yeah, it's the magnetic field that's making it all happen.
Yeah.
So it's basically the current, the vector of the current. So basically I times the length, right, that it's traveling, cross with the B field, IL cross B. That's basically what we've been doing. That ultimately relates to a basically two B fields, all right? But I can think of it like that. So IL cross B. So in this case, which way is that wire going to move? Given the way this is set up, which way would the wire be moving? So yeah, fingers go the direction of the current. The B field is from right to left. My thumb points up. So it would jump up, all right? That wire would jump up and it would just jump and then eventually be out of the B field and probably fall back down and jump back up again. It would be doing this kind of jumpy motion probably if we did that. All right. If I reverse the direction of the current, it would go down. Okay. All right. That's the basic idea. And so obviously if I put more current in here, what's going to happen? There's going to be more force, right? So, all right, that's what I have inside this DC machine. All right. So I want to think this through here real quick. So if I looked at the cross section of the machine that I showed you, basically what I see is I've got this sort of big air gap here. All right. Again, I exaggerated the air gap. And what I did was I showed what those brushes would look like. Right. So the brushes would be touching those copper strips. And basically the way this thing is set up is the current, in this case, I'm calling it I sub A. The A stands for armature, right? Is what we call that. All right. I sub A flows into this brush. And then it basically flows out on the top of the machine and in on the bottom of the machine. And it flows out the other brush. Okay. So the way this guy is set up is that means there's always current that's flowing out on the top and in on the bottom. All right. Now, what about the magnetic field here? In this case, what I did was I showed a motor that had what's called a field winding. All right. So we talked about field windings, on a synchronous machine. Basically, the job of the field winding is just to, in the synchronous machine or in the DC machine, basically is just to create a field that acts on the current. We have that same thing in the synchronous machine. You have the field winding on the rotor that just creates a magnetic field that makes voltages and all that good stuff. All right. In this case, the field winding is on the stator. All right. Now, in the motor that I showed you guys, it didn't have a field winding. How was I creating a field in the machine that I showed you? What did I have inside that? I had two magnets. So two magnets would work. I can have a north pole here. Basically, there'd be a north pole magnet on this side. and there'd be a south pole magnet on this side, right? So I don't do that here. What I did in this case is I put a current into this field winding, which would make a B field going this way, right? And you should be able to figure out the direction of that B field with the right-hand rule. What's going to happen is the B field is going to jump the gap here, like that. And he's going to jump the gap on the bottom, and then continue his pathway around the stator. All right, now, there's going to be a force on those wires, right? So if I think about this, force is IL cross B. So force equals IL cross B, where the B, I'm going to say, is just the field that's going around this thing. So somehow that B field is proportional to whatever that current is. All right. Now, one thing I want to think, if I told you this is a cross product, how do you figure out the magnitude of a cross product? How do I figure the magnitude of F? So if it's a dot product, it's the cosine. If it's a cross product, it's the sine. But if I look at this, if the gap is real small, the B field should just be jumping straight across. And the current and the B field should always be 90 degrees apart from each other. Field going this way, current going that way. There's a 90-degree angle between them. So if that's the case, the magnitude just becomes IL times B, right? Like that. All right, so I times the magnitude of B. Now, again, there's complex geometry to this whole thing, and we typically don't figure out, well, what's the relationship between the field current and B? We usually just say that B's magnitude is somehow a constant times IF. All right, some constant, depends on mu naughts and all sorts of things, right? But we usually just say that it's some constant. If I get a DC motor, oftentimes I can look that value up on the data sheet. All right. So what I have here is that this guy is specifically, if that's IA that the force is acting on, it's IAL times B time, which I said was G times the field current, like that. All right, now that's the force on the wire. What's the direction of the force on each of those wires? All right, so let's look at each individual one. Let's say I'm looking at this wire right here. Okay, I is going out, the B field's basically coming straight across and hitting at a 90-degree angle. So if I cross with B, my thumb is pointing that direction. If I looked at this one, I cross with B, my thumb would be pointing that direction. Here, that direction. If I was looking at this one, where would it be pointing? The one on the very top. I crossed with B, it'd be pointing straight to the right. So if I looked at it, right, it's going to go like this. Let me get the B fields off of there. Basically, the force on each one of these is going to be directly tangential to this thing. There's basically the same force on each one of those, basically trying to turn it in that direction. And as it turns, basically, the wires basically move their connection. Like this guy will start, this wire will move up to here, and this will start to connect to there. So it always maintains that connection like that. So there's a constant force rotating it around. And it's getting pulled around. The field winding is there to create a field that acts on the rotor. That's what's making this thing turn. Okay. All right. So the force is that. Since the force is, if there's N windings on this thing, what I end up saying is that the total force would be just the sum on all of them, right? So it basically becomes IA, IF, L, G times N, where N is the number of turns. And then if I want to go from force to torque, how do I do that? How do we get from force to torque? What was the way to get from force to torque? Force times distance, right? So the radius would be the distance here. So basically the net torque ends up being IA I, F, L, G, N, R, like that. Bunch of constants. All right, the important thing is I have the net torque equals, I'm going to write it like this, N, L, G, bunch of constants, R, I, F, I, A, like that. Okay, all right. Now move the R, I'm going to move the R. All right. This here is the B field. All right, so we had Newton's law, J d omega m by dt. Then the net torque on this thing is always equal to what minus what? So if it's a generator, it's mechanical minus electrical. If it's a motor, it's whatever the electrical torque is. That's what this is. This is the electrical torque. All right, I'm going to call it that. All right, minus the mechanical torque. All right, now, in steady state, what always is going to happen about these two things? And steady state means, what does it mean when I say steady state? What does it mean to be steady state? What does that mean to be in steady state? What's true about the speed in steady state? It's constant. So what's true about its derivative? Zero, right? So in steady state, this is equal to zero. All right, so this is the reason why I wanted to kind of do this. I'm going to take this motor here and all right. Let me stop my recording for a second. Okay. So if I spin the motor, we said we're going to get a voltage at the terminals, right? So what has to be in the circuit model? Okay, but what's in the circuit, the electrical circuit model? The changing magnetic field is creating a voltage, right? So what would be my electrical circuit model? A voltage source, right? And the voltage source, just like we had in the synchronous machine, is some constant times the speed, right? So some constant times speed. For now, I'm just going to call it C, I guess. Some constant times the speed. And I'll write my speed with omega m like that. Now, there should also be some resistance and some inductance to it, like that. So it's a lot like the synchronous machine model, exact same sort of thing. Now, real quick, I want to be able to figure out, though, if this machine was lossless. All right, I should be able to figure out real quick what the relationship is and see that it's proportional to speed, right? So what's the power into the machine? So if it's a motor, right? What's the power into this machine? It's the electrical power, right? So it's what times what? I look a voltage source up here. How do I calculate the power? VA, IA. Now, if this thing is lossless, there's really no losses, right? What's true about the output power, the mechanical power? It's the same, right? So how do I write that? Not as V times I, but as what times what? Torque times speed. Like that. All right, now, what do I already know? I know that the torque is equal to K times IA, right, times omega m, like that. So right off the bat, I get the current, the currents cancel out. This says that the voltage produced is K times omega m. So basically that same K that I derived right there basically is the constant of proportionality that tells me what the voltage is going to be. So if I look at this, what's in my circuit model is that K times omega m. So this guy really is a dependent voltage source, right? As it is in the synchronous machine. It's a dependent voltage source for that guy as well. What's it depend on? Speed, right? So a dependent voltage source can depend on other quantities, not just like a voltage or a current, or whatever. So if this thing spins faster, I get a bigger voltage there. All right, that's the basic idea. All right, now in general, we also typically assume that this inductance is pretty small. All right, it's not zero, but we usually make the assumption that it is. Right, it's a fairly reasonable assumption for what I would assume to do. All right, so problems with the DC machine are actually really easy to solve. All right, so let's say I had this machine. All right, and I actually did that for, I think in particular for one of these guys, right? I basically spun it to about 400 RPM. How did I do that? I basically put it on a drill and I spun the drill at about 400 RPM. All right, at 400 RPM, I got an open circuit voltage of 2.7227 volts. And I want to figure out what K is here. All right, so help me figure that out. How would I figure out the value of K? Yep, I do. So the test condition that I have here is that at 400 RPM, the voltage I measured was 2.7227 volts. That would basically mean if I took this machine and I spun the rotor, I had a turbine. In the case of what I did, the turbine was a drill, right? And I had the drill spinning at 400 RPM. I got that voltage. So how would I figure out what's going on? Looking at this circuit, what do I know about VOC in the circuit here? What's it have to be equal to if everything's open circuit? Yeah, K omega M, right? Because how much current's flowing in this thing? Zero. So there's no voltage drop across the R and the L, right? So I have my open circuit voltage VOC is equal to K times omega M. And what's omega M? Well, open circuit voltage, apparently I measured it to be 2.7227 volts. What's my omega M? What's that guy? How do I figure that out? Speeds?
The R, the revolution per minute in there.
Yep. Yeah. Okay. So I got 400 revolutions per minute. All right. How do I do the conversion to get that to radians per second? Yeah. So 2 pi radians is 1 revolution. And then basically I say that if in 1 minute, there's 60 seconds. All right. So you would do that to figure out your omega M. Right. And then if I solved this, what I work out to be, so revolutions cancel, minutes cancel, I get K equals about 0.065. Now, what are the units going to be here? They're going to be volts, seconds per radian. All right. All right. Kind of weird units, but I get that K value. That can also help me to figure out the torque. Okay. All right. Now what happens if I hook this thing up and I hook it up to a 10-volt source? All right. So what I did, so I'm saying I operated this thing, I tested it as a generator, spun it at 400 RPM, measured 2.7 volts approximately, figured out the K from that. And if you actually look at the way you would figure out the K, I used to do this in controls when I had to model out the DC machine. Basically what I would do is you spin it at a couple of different fixed speeds and you measure the voltage and you do a curve fit to figure out what the value of K is going to be. All right. The resistance in this case apparently is about 13.4 ohms. And I'm going to say the inductance I'm going to assume is about 0. Right. So if that's the case, and I hooked it up to a 10-volt source. Right. Now I want to figure out what's the current flowing in this thing. And in particular, I want to figure out what is the load torque. Under the conditions that I have right here, All right. I want to figure out what the load torque is. And I'm going to say specifically, I have 10 volts applied. Let's say my omega M is equal to, I don't know, 100. Actually, let me lower it down. Let me say it's 10 RPM. Say it's moving at 10 revolutions per minute. Okay. I want to figure out what's the load torque on the machine. How would I figure that out? Let's think about what we know. We know that this voltage here is K times omega M. We figured out K for this guy was 0.065. Okay. Okay, that's another amount of current in the systems. How would we figure that out? Yep. IA, just again, just circuit analysis, right? 10 minus K times omega M over RA has to be the current in that system, right? So again, I'd have to convert that omega M from 10 RPMs into radians per second, but I would get a number for that current. Now, what's the torque?
Would be the 800.
Right. So the electrical torque made by this machine in steady state, the load torque is really this guy, tau M, right? We said that I have, J d omega M by dt is equal to tau electrical minus tau mechanical. If I'm in steady state, the speed's not changing, right? Those two things balance each other, okay? And so what do I get then? All right, so basically in steady state, I can say the mechanical torque and the electrical torque have to be equal to each other. So once I have this number here, I would say the torque electrical has to be K times IA. So K times that expression. All right, now, what's the maximum amount of torque I could ever apply? I call this the stall torque. What's the maximum amount of torque I could ever have this machine make for me? Yeah, so like in this particular, in the case that I gave here, right, where I ran this motor on my test setup, there was a maximum torque I could ever get it to do. I could grab the shaft hard enough and it would stop, right? How would I figure out that maximum amount of torque? Because if I'm a designer, let's say I'm doing a robotics system or something like that, and I want to move a robot, I want to know what a stall torque is probably. I want to know what's the maximum amount of torque I could ever produce.
You have to know the minimum amount of torque.
And what's the minimum number? 0, stall, right? If omega M is 0, if he's not, so this is important typically because usually it's at stall conditions, omega M is equal to 0, right? He's just starting up. And so the maximum torque I could ever produce, if omega M is 0, what's the maximum current that can ever flow in this thing? What's IA max? 10 divided by RA. That's my stall current, basically. And so I would say my stall torque is K times whatever my maximum current is. And you'll often see that on a data sheet. What's the stall torque, right? Because to be honest with you, the one problem with this, right, is sometimes the stall torque is not actually as high as this says it is. Now, for this motor that's crappy with 13 ohms, it's probably fine. If the motor was super nice, and big motors tend to be nice because big motors, you couldn't feel this, but I could. When that thing was running even over there, I could feel it getting warm, right? So it was heating up. If I had a motor that was large, not like this little piece of junk, it would be highly efficient. So its resistance would be small. All right. In that particular case, the stall torque may be predicted to be enormously high, right? Higher than it can ever actually really be. So sometimes it's got some limitations physically. All right. One nice thing about this type of machine, all right, as the speed drops for a fixed voltage, just thinking about this real quick, something that's useful to think about. If I look at this thing here, if the voltage is fixed at 10 volts, at lower speeds, this guy can make quite a bit of torque, can he? Right, so as the speed drops down, he makes more and more torque. There actually is what I would call a torque speed relationship for this thing. So if this is my torque here, right, I can actually draw, so I just wrote that my torque was equal to K times the voltage that I applied minus K times the speed I'm going all over the resistance. If I were to plot torque versus speed, what I would see is there's some maximum value and it would slope downward. So I'd have an omega M max. And that I'm saying is at zero torque. Why does that happen at zero torque? For me to go to the max, what would the maximum speed be? How would I calculate the maximum speed? This is an important way to think about the way the motor actually operates, right? How would I calculate, looking at that circuit, how would I calculate the maximum speed it could ever go? Yeah, what would the maximum speed be that it could ever go? Well, basically it would depend on what's the maximum voltage across that voltage source, right? What would be the maximum voltage across that voltage source? 10 volts, right? So if there was no current going through this thing, I'd have 10 volts across that internal voltage source. How could I possibly have no current going through this? I have two voltage sources and a resistor. Well, you guys, well, if the voltages were the same, then what would make the voltages the same? This is an electromechanical system, right? That's the important point. There's a mechanical energy conversion that's happening, right? So what would the load torque have to be for there to be zero current? You guys had this right? So that in steady state, electrical torque has to equal the mechanical torque. What does the load torque have to be for no current to flow in? What would the load torque have to be for no current to ever flow in? What's the electrical torque proportional to? Current. So if the mechanical torque was zero, what would the load torque be? Or sorry, if the mechanical torque was zero, the electrical torque would be zero. So what would the current be? Zero. So if there's no torque applied, there'll be no current. This voltage and this voltage match each other. And that would be the maximum amount of speed I would ever have. So what we get is this thing called a torque speed relationship, where there's the maximum torque that occurs. So my torque max or stall torque, which happens at zero speed, and then my maximum amount of speed that happens at zero torque. Now, if you look at the motor that I had right here, when I spun it, when I just turned it on and I didn't grab the shaft, it had about 0.2 amps of current going into it, but there was no load torque applied. Why was it doing that? There had to have been a load torque applied. Where was it coming from? Just the brushes, all right? And whatever other friction's going on. And so there's bearings that hold this thing in place. There's some friction. In a really nice motor, so a big motor, right, that probably would be a lot lower. All right, so in other words, in this motor, I can't get all the way to this theoretical. I probably get to somewhere around here or something. All right, but this guy tells me the relationship. Now, one thing that's really nice about this, you ever been in a Tesla? Right, who's been in a Tesla? Right, so if you go in a Tesla, what happens when you hit the gas? It accelerates fast. All right, why is that? It's got a lot of torque at low speed, right? So when I'm starting out, when I'm at low speed, I'm in this range, aren't I? And that motor's producing a lot of torque, a heck of a lot more torque than a gasoline engine could ever produce at low speed, all right? So again, they don't have DC motors there, all right, just to be clear. But it's true basically for all motor types that you have a lot of torque produced at low speeds, right? So that's kind of an important concept to sort of understand. You've experienced that before. If you've been in a Tesla, you experienced that acceleration. The reason you experience acceleration because you got a lot of torque, right? Think about it. It's the moment of inertia times the rate of change of speed. That's why you're accelerating fast, because you got a lot of torque that's being applied. All right. Anyway, we'll stop there.